Calculus BC, we are looking at section 4.5, and it's really a review day where we're going to apply the information that we can get from the first derivative test and from testing from concavity and inflection points, and we can take all of this information and then make a graph. So that's some exciting news. Take a look at this function here, f of x equals x to the fourth minus 4x. In our learning target, I can use calculus to graph functions. Let's find all the local extrema. We could definitely take our first derivative and get our critical numbers, solve for them. Derivative is 4x to the third minus 4. If I were to set that equal to 0, we could add a 4 to both sides. We can divide by a 4. And without too much work, taking a cube root here, we only have one critical number, that is x equals 1. And using that first derivative test, if we were to check what is happening around x equals 1, we could say test a little bit to the right of x equals 1, maybe get x equals 2. If I were to test just to the left, let's be good to ourselves, test x equals 0. And of course, what we're actually doing, this is the first derivative test. We're going to substitute these test values into that first derivative. So we'd see f prime of 0 is 4 times 0 cubed minus 4. 0 to the third times 4 is just a 0. This is negative 4. It means our first derivative is negative on this interval, and that means my function is decreasing. Likewise, I can plug in a 2, and honestly, here's the great news. You don't even really have to work out exactly what this derivative is. You're honestly just concerned with whether the derivative is positive or negative. So you could, at this point, have just seen, hey, 2 to the third is 8. 8 times 4 is something larger than that minus 4. You know you're going to get something positive. So you don't always have to work out all the particular details. But please look at this graph. Look at the arrows. They're going to show you that you're going to have a relative minimum when x is equal to 1. So I'm going to do just a little bit of work here, and I'm going to say, we really need to come back to the function, and I'm going to plug a 1 into the original function. That's 1 to the fourth minus 4 times 1. And 1 to the fourth is just a 1 minus 4. This becomes negative 3. So what we can do right now is we know, look at that red little sketch right there. I can say that we have a relative min of negative 3 at x equals 1, but we have to give a reason. And the reason would be because f prime changes from negative to positive. Now we also could have said f, the original function, changes from decreasing to increasing. So we have a lot of information right now. We know there's only one local extrema. There is a local minimum or a relative minimum. Those words can be used interchangeably. So we also know where my function is going to be going down, decreasing, where it's going up. But we are asked to find inflection points. And it would be good to do some work right now. See, we already had our f prime. Let's find f double prime. F double prime, well, taking a derivative of 4x to the third, that's just going to become 12x squared. And then we're going to set that equal to 0. Yeah, obviously the derivative of that negative 4 is just a 0. I can divide by 12, take my square root, or square roots if you'd rather, or plus minus. Please understand this is not the second derivative test. Some students want to call this the second derivative test. It is not. The second derivative test doesn't have a number line whatsoever. It just will take critical numbers and plug a critical number into the second derivative to determine what is happening with curvature, with concavity. But this right here, you could say, well, what are we doing? Well, you could just say we're testing for inflection points. 0 is a candidate for being an inflection point, an x-coordinate. So I'm going to real quickly test some values around 0. And of course, we're going to test that into the second derivative. Look, the second derivative, plugging in a negative 1, we'll have 12 times negative 1 squared. And negative 1 squared is a positive 1. That's a 12. This is something positive. You know what? That means F is concave up. Concave up like a cup. Well, a lot of times kids will say, well, don't even bother checking it. It's going to change the sign. Guys, look, it's not. Watch out. You need to see this. We found a lot of inflection points already, but we're getting the same thing that we had even when we tested negative 1. The fact is, it's x squared. Wow, we've got this. What does it mean? There's no change in the sign of the second derivative. It means there are no inflection points. This graph is going to be concave up everywhere except at 0. And when x equals 0, my second derivative is 0. Wow. So no change in the curvature. Well, they're going to ask you to make a graph. And we can do that pretty quickly. We can say, hey, look, we have a point of 1 comma negative 3. We know this point right here is our relative minimum. And we know that our curve is going to be going down until it hits x equals 1. Then it's going to rise up. And very, very, very importantly, we know that the graph always is going to have some curvature being concave up. One real quick kind of an issue, you could say, what's happening at 0? You know, at 0, we'd have f of 0 equals 0. That's worth talking about. So very often kids might say, well, wait a minute. Hold on a second. Hold on a second. At x equals 0, you said there won't be an inflection point. No, there won't. But listen, I'm going to real quickly make a graph. And we know that we've got a relative minimum. We've got concave up everywhere except at this point 0, 0. You can wonder what's happening as we're going there. What in the world is happening? You can think this looks just like a parabola. It looks incredibly close to a parabola, doesn't it? According to the calculus. We know our curve is going to be going down. It's going to come up. At this point, 1 comma negative 3, that's our low point. We're going to be concave up like a cup, except right here. We've got to talk about what it means when your concavity is not positive or negative. When the second derivative, forgive me, I almost really misspoke. When your second derivative is not positive or negative, but your second derivative is 0, you could say, what kind of curvature is it? It actually means you don't have curvature. Guys, when you get a second derivative to equal 0, it's going to be linear. It's going to be more like a straight line. Now, look, I already typed this into the calculator. to really show you what's going on. You can see I just typed in the original function, and I actually did a zoom decimal. I did a zoom 4. And you can see what's happening. You definitely could say, hey, it looks like it's concave up everywhere, except at x equals 0, it goes straight for just a brief moment. There's no bend, there's no curvature whatsoever there. Everywhere else, you're concave up like a cup. So there's no inflection point. Definitely want to make that super clear. Our second derivative showed us that. We checked on the number line. There's no change in the sign of the second derivative. That means there's no change in concavity. But this is how, look how cool this really is. You don't even need a calculator to know what a graph like this looks like. Hope this is going well for you.